Hello dear friends, it's good to see you. Not long ago, I made a video about how an anti-Chinese computer managed to break through security breaches. This poses a risk to the entire internet. Well, I went through the video now and realized that essentially, this is a video that could have been split into 4 videos. That's why I'm telling you the 4 topics from the beginning and asking you to watch until the end. Because, as I said, it could have been 4 separate topics. Why did I do this? I wanted to understand it myself. I wanted to see what these security breaches are, how internet security works, and then I read about the Rivest-Shamir-Adleman algorithm. That was the first part. The second time, I wanted to see how these security breaches are hacked, how you manage to break into the internet. And then I read about the Shor algorithm, and I'm presenting it to you here. After that, of course, you had to read about the quantum computer. Namely, how does it manage to use the Shor algorithm and break these security breaches? Because a classical algorithm isn't powerful enough to do that. So that's the third part of the video. And last but not least, what's with this new result from the Chinese computer that supposedly broke the security breaches? So, my request is to try to stay until the end because, as you can see, there are basically 4 topics which could have been 4 different videos. A Chinese quantum computer with 1000 QBIS would have managed to break security systems. It is said that the entire cryptocurrency market would be at risk. Even Bitcoin could disappear. That's what the press says, but is it true? The news caught my attention. That's because it's related to quantum systems, to quantum computers. I knew that a quantum computer can, in principle, use an easy algorithm to break the security protocols used by all systems on the internet. So I did an exercise for you, but also for myself, to find out how security systems work, what an easy algorithm is. Even though I know what a quantum computer is, I didn't know how the quantum computer can break these security systems using an easy algorithm. And of course, what happened in China, sir? Is the security of the internet really in danger because of quantum computers, as the theory basically says? So I took some time to figure it out and hopefully to help you understand it too, I hope. First, we're going to talk about how these security systems work. So that's going to be the biggest part of the video, which will then lead us to the quantum computer. Easy algorithm. And at the end, we'll talk about what's happening in China. I'd just like to make an observation at the beginning because I'm not a specialist in these security systems. And I've seen that there are a lot of things from practice. What I tried to do was to understand the logic behind these security systems. But I'm sure that many of you, a lot of you, maybe even work in this field and know much better than I do. So I hope I haven't said anything wrong. If there are any mistakes, please write them in the comments. I don't know if I'll cut it from the video because I don't know what I'll do. But on the other hand, I admit from the start that this is a simplification, an ultra simplification of what actually happens in practice. Because indeed, the field is extremely complex. I also took a look, I opened the door a little, took a peek and tried to understand as much as I could. Let's get started. The first thing I learned, let's say I want to send a 100 megabyte file. Here's how it works. First, you choose an encryption key. This usually has 128 bits, which is a number with almost 40 digits. Then the file is split into small pieces called data blocks, which are also often 128 bits each. Each block is encrypted using the same key so that all the pieces of the file are transformed into an individual form. Impossible to interpret without the correct key, but this encryption key isn't just left out in the open, God forbid. It is in turn encrypted through a separate process called Rivest-Shamir-Adleman. This is the most important step in today's story. The encryption key of the file is itself encrypted with another key, and in this form it becomes completely useless to anyone who receives it along with the file. In short, Rivest-Shamir-Adleman is a system that encrypts the key itself, making it impossible for intruders to use. In the end, the encrypted file is sent along with the secured key, which is itself encrypted. The encrypted blocks are combined into a fully encrypted file, and the Rivest-Shamir-Adleman encrypted key is attached to it and sent to the recipient. Our friend to whom it is addressed. the recipient will be able to decrypt this key because a long time ago they were sent another special key called a private key, which allows them to decipher it. That's why, even if someone intercepts both the file and the protected key, they can't reconstruct them because they don't have the private key needed to decrypt the key used to encrypt the file. University, how is it encrypted? Each portion of the file is encrypted with the encryption key. You take a portion of the file and follow some standard procedures. For example, additional characters are added and the data is split into matrices. Then operations are performed on those matrices based on the bits from the encryption key, rotation operations, multiplication with fixed matrices, and so on. I imagine it's like a deck of cards. It's a deck of cards, right? The cards are randomly arranged in a specific order. You can write it down on a piece of paper, and with each operation, you cut the deck of cards in different ways, depending on the bits you have there. And you realize that after you've cut that deck and shuffled it, in the end, you'll have a different order of the cards. So when you read this order of the cards, you have no idea how the cards were originally. The same thing happens with the message when it gets mixed up with each operation. This, of course, is the first part, because the person who receives the message wants to read what that message was. So he has to decipher it, and to decipher it, he needs the key with which the message was encoded. That's what I was saying. It's called symmetric encryption or something like that, right? And how can he do that? In the simplest of the cases that I found? Well, basically, once he has the key, he applies the operations in reverse. Yes, it's just like with the deck of cards. You have that specific one. Sorry, yes. And you know what operations were done, so you do them in reverse. And in the end, you get the cards in the original order. It's the same with the message. You apply the key in reverse. All those operations on matrices are in reverse. And in the end, you end up with the original message. By the way, I forgot to mention this. With each operation, yes, the operations are done in such a way that the complexity is maximized. I mean, just to make sure it doesn't end up like the message Hitler sent with the Enigma. Do you remember World War II? Why did people decipher the Enigma? Because every time those Germans sent a message, they always ended it with Heil Hitler. Heil Hitler. And then the English sat and thought, man, how can we decipher this message? Man, these guys definitely write Heil Hitler at the end. And that was, how should I say, their Achilles heel. Based on those things, they started to decipher. Let's get back to this thing, okay? So, every operation that is done, pay attention. It has to complicate the message in such a way that the true meaning of that message is lost. Now I take the scrambled message on my computer with the key. Yes, the scrambled message. I send it across the internet to reach everyone, especially the person I'm interested in. The message? Yes. So basically anyone who can read that message doesn't understand anything. But attention, now I want to send the key to the person as well so that the person can decipher the message. As I said, he uses the key, goes in reverse, and recognizes the message. I don't want to send the key, but I will send the key securely. So the second step is to send the key securely. Attention, only this 128-bit key. In my case, the most common method is called Rivest, Shamir, Adelman, which comes from the names of the authors. Rivest, Shamir, Adelman. How does the Rivest, Shamir, Adelman method work? The mathematics behind it is extremely complex and difficult to understand. What I did was to reproduce the steps. And in short, the steps are in this small example, after which, if pay attention, we will also discuss a real example. You can see how complex this problem is and how smart the people who did this are. The steps start with choosing some prime numbers, two prime numbers. In this case, I chose 61 and 53 here. Actually, in this case, CRGPT for me. By the way, I checked this thing on CRGPT and on a special YouTube channel that explained this procedure in detail. But I took the examples with CRGPT. Okay, so you start with two prime numbers. In this case, 61 and 53. These two prime numbers are multiplied, and you get a number. Once we have this number, which is just the product of two primes, we calculate the phi function, Euler's function, which is phi of n equals p minus 1 times q minus 1. So in this case, 60 times 52, and that means 3,120. After that, we choose a public key. A public key is a number that we will write on the window so that everyone knows it. We give it away for free on the internet. In this case, it's 17. Now we're interested in calculating a private key, which we keep just for ourselves, and we'll also give the same private key to others, of course, to those who need to decrypt the message. How is D calculated? D is determined so the public and private keys multiply together, divided by Euler's number, calculated from the two prime numbers, meaning calculated from P and Q. The remainder of this division should be 1. Now, it's very interesting that we can throw away the numbers P and Q. We only leave the chosen number N on the computer. We also leave the public key, which is everywhere, and the private key. And now we want to send a message, in this case 1, 2, 3, and of course we want to send it securely. How do we do that? We encode it with formula C. So the message we send is M123 raised to the power of E. What is the public key? Modulo n, meaning n, is that number we chose at the beginning as the product of the two prime numbers. In this case, C, what we will send is 123, which is the message we want to send, to the power of 17. The public key is 17 modulo 3233, because the number 3233 that we chose at the beginning was 3233. And if we do that calculation, we'll get 855. Basically, the remainder of dividing 123 to the power of 17 by 3233 gives us 855. And now, what do we send to the public space for everyone to see? And now, this public complicated message, let's say, which we marked as C855 reaches everywhere in the world. People see that message and don't understand it because they can't see what's behind it. 1, 2, 3. Yes, but we also reach the person who has our private key. And that person needs to find the original message 1, 3 using this key. How does he do it? Well, he does it with the following formula. The message M, meaning the original one, should be C, meaning what did he receive? 855 raised to the power of D, the private key, then modulo N, the chosen number. In other words, 855, which is the number he received, to the power of 2753, because 2753 is D, the private key, modulo 3233, because the initial number chosen was 33. If he does the calculation, he gets 123, yes. So he recovered the original message using the private key. I forgot to mention that. Or maybe when we say that the public key E is sent over the internet, it's not just that number E, which in our case was 17, but it's sent together with the initial number 3233A, really big one. So both E and N are public. What isn't public is just that number T, which is the private key. To get an idea, let's move on to the numbers that are actually used on computers. When securing a key, he starts with two prime numbers, which, mind you, are not as small as I mentioned here, but each has up to 1024 bits, or maybe even 1024 bits. That means a prime number chosen by the computer has about 300 digits, and it chooses another number also with about 300 digits, and it multiplies them. And it gets a long number, that N, which is the product of the two prime numbers, and pay attention, it has almost 600 digits. The public key is that number 17 that we chose, but I understand that the same number is always chosen, namely 65,537, which essentially is a prime number. How big is the private key then? It will also be a number, yes, which in bits has about 2,000 and something bits. And in digits, it has about 600 digits. And now the cool part is what calculation the computer has to do when it sends the message. Well, it has to calculate M3 to the power of E mod N. Here, M is the message we want to send. And he said that we want to send a 128-bit key. So let's say approximately 40 digits. So that's M, that's 40 digits to the power of E, which is the public key. So to the power of 65,537 modulo N, which is the modulus of a number. So about 600 digits. This will be the message sent, and the one who decrypts has a task that at first glance seems impossible. He has to calculate E to the power of D modulo N, where E is now 65,537 raised to the power of D. It's a number with 600 digits. Can you imagine what he has to calculate? And after he does this calculation, he has to calculate the remainder of this number divided by the chosen n, which is also a 600-digit number. I hope this didn't confuse you. I've gone through these calculations about, I think, virtually, because the steps are very clear. I mean, it's clear what you have to do. And I found that with generative pre-trained transformer, I also give you the Python functions you want to implement. So basically, you can do this at home too. The problem I had, the first problem was, sir, how is the computer able to calculate something like this? 65,537 to the power of a 600-digit number, and to find the remainder when divided by another 600-digit number. How does it do this, sir, right? The second point, which is important for our quantum computer discussion, involves the two initial prime numbers. But first, let's see how the calculation works, as it's key for a simple algorithm. What's the method? The method finds periodicity in numbers that are powers of 2, as shown in this example. I'll leave the link in the description. We want to find out what 331 to the power of 571 modulo 1000 is, so the remainder when divided by 1073. First, we only choose the power of 2 as the exponent of the number 331. In the first column, we have the powers of 2. In the second column, we have 331 to that power modulo 1073. We don't need to do the full power calculation for each line. We just use the result from the previous line, which we always raise to the power of 2. Well, mathematics, what do we notice at some point? That the result 552 appears again, which was there before. This shows a periodic pattern in the powers of 2 from the row with power 3, 8 to the row with power 9552 in the table. The results will repeat in the future, so we don't need to do the calculation anymore. However, what interests us is 331 to the power of 571 in the example. The last step is to express 571 as a sum of powers of 2. Not all of them. Be careful. Then we need to collect the values from the previous tables and multiply them. In the end, 331 to the power of 571 modulo 1073 will be 829. That's how we got to Shor's algorithm and the quantum computer. How can we break another kind of system? Essentially, it can be broken. If someone looks at the number n, that huge number with 600 digits, and they know that number is the product of two prime numbers, namely p and q, if they manage to find those p and q, yes, then they could use the public key to reconstruct the private key, just like the person who messaged his computer did. And this is where the quantum computer and Shor's algorithm come in. Let's first explain Shor's algorithm using, well, classical understanding, and then we'll come back to the quantum computer. Shor's algorithm. It starts from this image that you saw earlier, where you notice that when we work with remainders of divisions, periodicities appear. You can see here, for example, the remainders of dividing the powers of 2 by 55. First, 2 to the power of 0 equals 1. Dividing by 55 leaves a remainder of 1. 2 to the first power is 2, so the remainder, when divided by 55, is 2 to the 2/0th power gives a remainder of 1 when divided by 55. Just like at the start. This is what we saw being used before to calculate the remainder of divisions when you have very large numbers. But now, we want to use exactly this thing to break a very large prime number into its two component numbers. We use Shor's algorithm. Shor's algorithm starts from the fact that the following function is periodic. So we have this. F is a function of a, which can be any number, to the power of x modulo n. N is that large number with 600 digits that we want to break down into its prime factors. This function of x is periodic. In the previous example, the periodicity was 20. R equals 20, with R being the periodicity. Shor's algorithm relies on this function's periodicity. He says, to which number n should I factor? In our case, it would be that 600-digit number, which should be factored into two prime numbers. And Shor tells us, okay, choose the number a. What is any prime number? You can try once, you can try a second time and a third time, and most likely you'll find the number that fits. And that means it doesn't work the first time. Raise this function to the power of x. Since it's a function of x, calculate it for x equals 1, 2, 3, 4, 5, etc. How far can you go? Build this function to x modulo n, and you draw the remainder like this. And you'll see that a periodicity of that r appears, and for now, we're interested in what r is. In the previous example, the periodicity was r, about 20. If you found the periodicity of this r, check that it's even. If it's not even, that's fine. Pick another a and try again. But if r is even, there's one more mathematical condition to meet. Calculate two numbers, a to the power of r divided by 2 minus 1, and a to the power of r divided by 2 plus 1, and then calculate the greatest common divisor of these two numbers. And as Shor tells us, you will most likely get one of the two prime factors of the large number n. You see here that there is still a technical problem because at this step, Shor tells us, calculate the greatest common divisor between two numbers, both of which are large. N has about 600 digits and a to the power of r divided by 2 minus 1, which will also be very large. Yes? But on the other hand, it seems that there are methods by which you can calculate the greatest common divisor. Okay, and what's the problem with the algorithm? Sure, why can't classical computers do this? Well, classical computers can't quickly find that r, that periodicity. Why? Because they would have to do a to the power of x and take x as 1, 2, 3, I don't know what. And if n has 600 digits, you realize that the power and digits. Do you realize to the power of I don't know what? And if n is the number of digits, do you realize that to the power of x and 2, 3? I don't know. If it has 600 digits, do you realize what kind of number that is? Thank you. I don't know if anyone is going to track them with these security things. They were new for me too. But I wasted so much time that with the old computer, I really don't have time to talk that much anymore. But I'll tell you what the essence is. The essence of a computer is that it can do processes in parallel. And pay attention, it has to be the same operation that it can perform in parallel. So what does that mean? Let's say you have a photo album and you want to see where there are cats. And you always use the same algorithm. On a classical computer, how do you proceed? You take the first photo, process the first photo, and say it has a cat or it doesn't have a cat. You take the second photo, process the second photo, has a cat or doesn't have a cat, and so on. And let's suppose that in all these photos, there's only one photo where you have a cat. How can you do this in parallel with a quantum computer? Well, you do it like this. You take the photos from the album and put them in a quantum superposition state. So you create a quantum state, which is a quantum superposition of all of them, and then you process this quantum superposition state with the quantum algorithm, which is essentially the classical algorithm, but it works on this quantum part. That means that at the output, it will also give you a quantum state, which is a quantum superposition of the results of the individual processes. And what you have to do at the end, you have to do one more operation, because you know what happens. Quantum measurement causes collapse, so you can't observe all individual states. You only get one answer, and then you have to do a smart operation at the end, so that yes, the operation here is smart, to give you the answer on the quantum state to what you want. In this case, that smart operation has to be okay. I have this quantum state that has 0, 0, 0 everywhere, and somewhere it has a 1, because there was only one picture that had a cat. Let's say yes, and this operation has to tell me, okay, where the 1 is found, we say 0, the location where the 1 is found. Well, if you make a quantum measurement using that operation, the result of the quantum measurement, which is also probabilistic, that result will be the location where it is found. The picture with the cat with a very high probability. And how does the Shor algorithm perform this operation when implemented on a quantum computer? Well, it has to build this function x modulo n. Who is here? N. Is that very large number with 600 digits. A is the number, and x is 1, 2, 3, 4, 5, and so on, going up to very, very large numbers. What does that mean? It means that he first has to create the quantum superposition state, right? And here he puts x in the first quantum superposition state. X equals 1 here, x equals 2 here, x equals 3 here, x equals 4 here, x equals 5. And all of this is a quantum superposition state. So he has to find them simultaneously in all those spheres. What do we need to do next? Take the function a to the power of x modulo n, a function of x, and input it into the quantum processor. And normally, if it were classical, this function would be applied to 1x equals 1 or to 2x equals 2 or to 3x equals 3. Now, it is applied to the entire quantum superposition state. That means that once you pass the whole quantum superposition state through that processor, at the end, you will have as a result a quantum superposition state. What will the result be? That means here, the result will be a to the power of 1 modulo n, which will be that number in the next one. In the second result, it's a to the second power mod n. In the third, it's a to the third power mod n, and so on. It's just that you have all these results, you have them all at once because you processed in parallel. But they are found in this quantum superposition state. Well, and in the end, you're only allowed to do one smart operation to make a measurement, so a quantum collapse, and get what you want. But what Shor chooses to do is a Fourier transform, and then a frequency measurement. And after these two operations, yes, he makes a measurement. So the frequency measurement is a measurement, and as a result of the measurement, he obtains the periodicity of the initial signal, meaning that R he wanted. To be honest, I imagine it like with particles, namely if here is the first result, the second, the third, and so on. Yes, these results after processing will be like the position of the particle. And if I look at the wave function, I'll have something like periodicity, right? And for the particle, how can I get, if this would be the wave function of the particle? So if these are the positions and this is the wave function, how can I measure the periodicity of the wave function? Well, I make a momentum measurement on the particle. So if I measure the particle's momentum, I'll find out the period precisely. The big advantage of this quantum computer is that we were able to obtain the periodicity of that function, let's say Alushor's, and by having that periodicity. After that, we can continue the algorithm. And in this way, we can find P and Q, which are the two numbers that make up n, the big number n. And with that, we have finally reached the news that was in the press. That the Chinese managed with a quantum computer of 1000 qubits to break such a key secured with an RSI system. Then they proceeded using a lightweight algorithm, as I explained earlier. The problem with such news is that this, let's say, breaking was done for an RSI system of 22 dB. What does that mean? It means that big number, which is made up of two prime numbers, had 22. That means 7 digits, approximately. 7 digits. How much is that? 1 million? So essentially, that quantum computer managed to take the big number n, which this time had only 7 digits, so it was 1,700,000 something. And it managed to find those two prime numbers P and Q from which it was composed. Well, you realize right away, after everything we've discussed here, that this doesn't pose any problem for those current systems, because the current systems use 2048. So that means that big number n, which is made up of two prime numbers, has about 600 digits. Well, this quantum computer managed to factor, yes, a number that had only 7 digits. Well, of course, this can be done very quickly with a regular computer as well. This means that at the moment, we have no problem with cryptocurrencies, and of course no problem with Bitcoin either. But be careful, this doesn't mean that it couldn't happen in the future. What the Chinese have shown is that technically it is possible. So, technically, sir, you can indeed create that state of quantum superposition for Shor's function f. I showed you that you can apply that quantum processing for Shor's function f. That in the end you can do a final operation, a Fourier transform, and make a quantum measurement to find that number. Well, what was the periodicity of that function? Personally, I don't see a problem, at least in the short term. On one hand, because these quantum computers don't seem to be advancing. Explosive? Yes, so there's talk about quantum computers. with more than thousands of qubits, and well, this number of qubits will keep increasing, but it's not something explosive. And the second thing I want to say is, I've read that even the classical security algorithms which now rely on RSI, yes, even these are going to be changed so that they are secure even for RSI, quantum computers. In other words, internet security experts know quantum computers are coming with potentially hundreds of thousands or millions of qubits. Later, this will cause serious problems for this system and RSI, but I read that there are already classical solutions which are very, very resilient, even for the quantum computers that are about to come, and, well, which are very, very complex. In short, don't fear these things. Now, a quick note about this video. I'm drawing my own conclusions and sharing them with you. Again, it took me a lot of time to do this, and it took a lot of time because I had to learn it myself. So that thing with RSI, I had to learn it myself. And I realized that this is one of the problems with these videos, because I'm not only talking about what I know, I have to think. So, alright, in the future, how do I manage, sir, to make freely spoken videos in much less time? And so one of the lessons I learned today is that I will probably have to pick topics that I already know beforehand. I don't know when this video will be released, since it was recorded earlier. It might appear in 3 months. In the meantime, I've already made some short videos, and I've found my own way of working to make those videos where I speak freely and that are still short. And with that, we've reached the end of today's video. As usual, if you haven't subscribed yet, you can do so by clicking the subscribe button. I'm Christian Presura. You guys are cool. You know you can also find me on Patreon, where if you subscribe at a higher level, you can get answers directly on WhatsApp to the questions you have for me. Until next time, I'm Christian Presura. You guys are cool. All the best. Goodbye.